Hello, I'm going to take you through Spectrum Analyser, which is a tool that's been developed to help reverse engineer ZX Spectrum games. The first thing I'm going to do is take you through getting started, and what we're going to do is we're going to have a look at disassembling and reverse engineering Jack the Nipper 2. So the first thing I've done is opened up the folder where Spectrum Analyser is installed, and what I'm going to do is I'm going to put the Jack the Nipper.z80 file in there. You can see there's already a Starquake which came with the program. So what I'm going to do now is I'm going to start it up, and as you can see it started up in Sinclair Basic. What I'm going to do is I'm going to load the game. So what I need to do first is to do new game from snapshot file, and what that will do is it will create a new game disassembly from a snapshot file. So let's take Jack the Nipper 2, and as you can see it's loaded up now. Now we've got various views here. We've got the Spectrum view, which shows us what's going on in the emulator, and we've got the code analysis view down here. Now these are the main two views that I'm going to talk about in this video, because they're kind of like the most important ones, especially when it comes to getting started. Now when the snapshot is loaded, it's not actually running. You have to tell it to run. That's what I'm going to do now. So I've got it running now. You can see it running in the Spectrum view, and what I can do now is play it a little bit. Just to, make sure everything's working. Okay, so now what I want to do is figure out how this game is working. So I'm going to break into the program. So I've stopped it running now. Now the approach I take for reverse engineering games is I kind of look at the program as something that takes inputs, and it kind of processes those inputs and generates outputs. So in this case, the inputs are going to be things like the controls, the keyboard, and the output is going to be things like the screen display and the audio. So I'm going to concentrate on the screen display. So what we've got here is a program that's been run. It's in a stopped state, and it's got a screen that has been generated by it. So what we can do in the Spectrum view is we can look at each pixel line on the screen and find out what bit of code wrote that particular bit of screen graphics. So what I want to do is find out how the background's been drawn. So the first thing to do is to find a square on any point on the background, and if I double click on it, what it will do is it will take me to the instruction that was used to write that particular pixel line to screen memory. So you can see here we've got an LD to the contents of HL, so that writes a screen pixel line. So what I'm going to do is I'm going to put a comment there saying write pixel line, because we know that that is right to the screen. And if we actually look here, we can see that piece of code is repeated, and this is quite common in Spectrum games where they unroll the loops and they actually call the same thing several times to save having a loop and a branch. So if we have a look at this, we've got several lines that write to the screen. So what I'm going to do is I'm going to label them all. So we know what's going on there. So let's change that comment to say write line 4, and then we go write line 5. Now it's important to remember that because the Spectrum screen is like a bitmap, each byte is actually each byte is actually 8 pixels, because 1 bit is 1 pixel. So we can see with this particular bit of code that it's writing. Oops, I did that in the wrong place then. I need to be more careful. We can see that it's writing 8 pixel lines. So essentially this is writing a screen character to the screen. So there we've got 8 lines being written. So we can see they're written to the screen, but we need to find out where that data is coming from. So we can do that by finding out where does it get A from. Well, it gets A from the contents of BC. So let me just put that in there so we know that it's fetching a pixel line that's going to get written to the screen. Now if you look up, so where does it get BC from? Well, we can see here B and C get moved from HL into BC. So we just put a comment saying that's what's happening, and then we need to have a look and see how HL is actually getting generated. Well, we can see that that's in these lines here. Now one thing that's quite interesting here is we've got these 3 add HLs. Now this happens quite a lot in Spectrum games because the Z80 couldn't do a multiply. Often people do multiple add HLs if they want to multiply by a power of 2. So we can see here there's 3 in a row, so that's actually multiplied by 8. And that's significant because we know it's writing 8 bytes. We can see that further down. So it's writing a character, and now it's getting to a character. This is generating an offset to a character in memory. So HL starts off as A, gets multiplied by 8, and then gets added to this base. So, and this is where the data for the screen is coming from. So we can see here that that must be where some character definitions are, and the offset is a multiple of 8, and it's getting added to that base address. So essentially A must be the character number, then gets multiplied by 8 and gets added to the base address. So we can write that down here. And then we can add offset there. Now we know that this is a base character address, so these are the background character definitions. This must be where they're stored. So I'm going to stick a label in there by pressing L. It gives me a label, and then I can say that's where the background characters are stored. Okay, now interestingly, what we can do here is we can actually have a look at this visually. So we've got another screen here, which is the graphics view you can see here, and that's kind of a bitmap representation of memory. It kind of shows where memory is being written and where it's being read and where it's being executed. So writes are red, reads are green, and execution is yellow. So we can see things like there's a font there, and there's some other stuff. But what right now we want to have a look at these background characters. If I right click on the first address there, I can do view in graphics viewer, and then we can see here that the first character is blank, and then that's followed by what looks like various images. Now what we can do is we can view those in a bit more of a magnified way by actually formatting this memory, because you can see the memory as it is here. It's just a series of hex numbers, and what we really want to see is a bitmap. So we can use a format option here, and we can format the memory to be a bitmap. We can say we want it to be 8 by 8, and then if I click format, that will kind of create a grid. Now this first one is empty, so that's giving us an empty grid, but we can go to the next one, and if we do format, we can see there's a pattern there. And if we go to the next one, we can do the same thing, and then there's another pattern. And I can keep doing this. Now I've actually got a button here that does it faster, where it'll actually auto increment it, so I can click on that and I can do that, and I can keep pressing that. But I can keep doing that if I want to, but I think I'm just going to do that and go back to the code. I mean, I can flesh this out a bit more later on if I want to. But anyway, we can see here now that because I put the label in there, it's actually mentioned the label there. So what we've got here is we've got a character number that looks up from here and then draws on the screen. But the question is, where does it get this A from? Well, we can see just above it loads it from memory. So let's comment that. So you do a slash to do comments, which is like the C++ slash. I probably should change this to make it look more like an assembler comment, but it's just like a C++ one at the moment. So that reads in the character number, and the question is, where does it get that from? Well, we can see it further up here that there's an address there that it uses, and then that's where the screen address is there, which presumably it uses to write to later on. That gets pushed on the stack, and then we've kind of got a couple of values in here. Now, interestingly enough, we can see that value there is 20 in hex, which is 32. Now, I know that Spectrum's 32 characters across, so my guess is that that's a horizontal loop. I can actually change the operand type to be decimal so it's easier to read, so that's 32. So I think that's a horizontal count, so I'm going to put that in a comment. Now, if I'm wrong, I can change the comment again, but based on what I can see is happening here, it does look as though this is something to draw the whole screen. And if we look a bit further up there, there's another B, and that's set to 14H. So if we change the operand type to decimal, that's 20. Now the Spectrum screen is 24 characters high, but if we look at this screen here, we can see that the game doesn't cover the entire screen. There's a status panel at the bottom, and if we look at the status panel, that is 4 characters high. So 4 of those 24 characters is this, which leaves 20 left for the screen. So I think that is a vertical count. So I'll put that there. And we can probably see that if it is B that's getting loaded, there's probably a D, J, and Z knocking around somewhere, or 2. There we go. So that is probably the horizontal counter. No, so that's the horizontal count there, the horizontal loop. Yeah. So we can change that label to be background H loop, let's call it. And then we think this is probably background V loop. Now if we look down, we can see that there's the horizontal loop there and there's a vertical loop there. So we've kind of got something that loops over every character in the screen, at least in the top 20 characters of the screen, and draws it to the screen. So we've kind of got our loop there. We've got something here where it fetches characters from, and if we look here, it fetches them from DE there, and then let's have a little bit look further down, and look, DE gets incremented there. So it iterates for every character on the screen, left to right, top to bottom, and every time it pulls a character from DE and increments DE. So it looks to me as though what DE initially points to is a character map of the screen. Now let's just put a comment in there to say that increments character pointer. So if you look back, and this is after the background characters in memory, so I think this is a character map. So if we go there and put a label in, let me just get off that mode. So we put a label in here, and call it background char map. Yeah, and that's a number of character indices. Now, as before, this is just a load of hex numbers, and we probably want to have something a little bit more visually representative. So we can use the formatter again, and there's a character map mode here. So we remember now that it was 32 by 20, wasn't it? Yeah, and we want it to be a character map. And if we do format, we can see there that it's visualizing it as a character map, and because it doesn't draw anything that's a 0, you can see where the holes are. And if we actually look at this character map and compare it to the Spectrum screen, we can see that it does seem to represent what's actually happening on the screen. Sorry, pardon me. Now, just to make sure, what we can do is we can continue running it now, and let's try going between two screens, and you can see that it gets updated with the new character map. So we know that that's definitely giving us a character map of the current screen. Right, let's go back. So I guess the next question is, how does that character map get generated? Now if we go back and look at it, we can run the program again and flip the screen. And you can see we've got these arrows that appear, and there's a green one saying it's being read and a red one saying it's being written to. And what we're interested in, we know where it's getting read, we want to know where it's getting written to. So what I'm going to do is I'm going to break again, and I'm going to click on one of these lines, and we've got some information on a particular memory address where it gets read. Well, we know about that one. There's some other places it gets read but we don't really know about. But what we're looking for is where it gets written to, because we want to know how this character map's getting generated, because it must be getting generated every time you flip screens, and it must be getting fetched from some larger data structure that has the entire game map in, and that's kind of quite interesting. We want to see what that is. So let's have a look and see where this is getting written. Okay, so this is the first write that we found. Now it's getting written to 0 here, so this is kind of a sign that this must be where it's getting cleared. And if we actually have a look, we can see that that's actually quite a short loop there. So we get the address of the character map there. BC gets set to quite a large number, but we can actually again do decimal, and that we know that's clear in the character map. So let's just then that increments the pointer, then that decrements BC, and then it seems to be comparing, doing an OR between B and C. So this is basically a 16-bit counter, and I've seen this in a lot of games where to see if a 16-bit counter has reached 0, you kind of OR the 2 bytes together, which is what's happening here. So this is yeah. So this is a loop to clear the character map. And we can see this is in a function, and this function pretty much clears the screen. Not entirely sure what this is here. That's something we can maybe look at later. But I'm going to change this function name to clear screen char map, like that. Okay, so I think we found one of our writes here, and if I kind of go back, we've got one write which is clear char map in the clear char map loop. Now we've got another one here. Now maybe this one's a little bit more interesting. So what have we got here? this is loading something from memory and writing it. So this could be where it's actually generating the character map. So let's have a look. Let's put a comment in there. Now, we've seen something like this before, haven't we? Where we've got several writes. So this is an unrolled loop again, and we've got another one here. So let's have a look. We've got quite a few of them actually. Actually, I've missed one there, didn't I? Whoops. Let's change that to 3. So that looks like it's the first one. So we've got 1, 2, 3, 4, 5, 6, 7, 8. No, okay, there's quite a lot there. Looks like there's over 10. So let's, rather than count all those up, let's have a look at some of the lines before. Okay, so we've got some add HLs there again. Now we saw those before with the character lookup. Now this is 4 add HLs, which is multiplied by 16. So let's put that in, because I think that gives us a bit of a clue as to how many writes we've got down there, I think. And then we've got an offset that's getting loaded. So we've got a base and an offset. So the and then we've got, I reckon, there's 16 writes here. Because what I think is this is some kind of block that gets written to the character map, probably from a room definition of some kind. And if you actually look at this map, we can see that it does kind of look like it's made by 16 by 16 or 4 by 4 blocks. 1, 2, 3, 4. 1, 2, 3, 4. Yeah. So that does kind of look like we've got 1, 2, 3, 4, 5. So yeah, so you can have 5 vertically and 1, 2, 3, 4, 5, 6, 7, 8 horizontally. So it looks to me as though the screens are made out of these 4 by 4 blocks. This is the block index. It gets multiplied by 16, offset from this. This, I'm guessing, is some kind of block lookup. The first one looks like it's all zeros, which kind of makes sense. So I'm going to call it something like map blocks. So that's like, yeah, a big load of 16 entry blocks. I mean, we could probably look at these as though they are character maps, because it is a kind of a character map. It's a small character map. So what I could do if I wanted to, maybe I will, is have them as a 4 by 4. And what we can do is we can give each one a label as well. So if I do format, that's empty, that one. Then take the next one. We can kind of format a few of them. And you can see they kind of look a bit like building blocks for a level, don't they? I mean, the best thing would be is if this view could actually look at the character definitions, draw the character definitions in there, but you know, that's probably another job for another day. I've kind of auto-generated labels here, but You can go through and rename them if you wanted to, but really what we want to do is just make sure that label's there. So it takes the block index, multiplies by 16, and then writes to the character map. That presumably there is some kind of loop count. Let's just see what it does after. Yeah, that does a loop back. So if we have a look at that loop count again, there it is. Let's put that into decimal. Okay, so that's 29. So what was it we had? Yeah. 1, 2, 3, 4, 5, 6, 7, 8. 8 by 5. Yeah, that doesn't quite make 29, does it? I wonder what that's all about. Maybe it's something else to look into. Okay. Yeah, that's probably something I need to have a look at. Oh no, wait a second, we've got some other loops here. Maybe we should have a look at that. That looks like it's a horizontal loop there. And that looks like it's a vertical loop there. Because we know it was 8 by 5. So okay, so let's... make sure we've got those in there. Then we've kind of got... Okay, that's what the background character map is. That's where we're writing to. And then this is something, an address in memory that's outside of screen attribute memory, actually, just outside. And we've got some add HLs there again as well. That's quite interesting. And then we've got the call to clear it. So this must be something that clears the screen character map and then it writes to it. Kind of makes sense, doesn't it? And then we've getting that block index that's got from somewhere. Let's have a look and see where that comes from. That's reading some value there. Okay, that looks like it. So it does some checks there. It backs it up in the shadow register there. Presumably it restores it yet there. Then it pulls it in. Okay. And we've got some logic here. Now one thing is that code that doesn't get run doesn't get marked as code. But when we look at this, we can see it's a JR0. So every time this is run, the 0 flag's always been set. But there is code there that can run. If it's not set, it just hasn't been run yet. So what we can do is you can say that's definitely code. I can put the cursor over it, press C, and that actually just disassembles it. So we've kind of got yeah, an alternative bit of code there that doesn't get run, but it may get run on some screens, I don't know. So where were we? Yeah, that's where we get the block index. And it gets that from DE. So let's have a look and see a DE is generated. I'm guessing DE gets incremented in this loop, in this horizontal loop. That's a different DE. probably a pop there. I can't spell. Right, okay, so that gets incremented there. Then we have our, looks like our horizontal loop. Yeah. So I'm going to call it horizontal block loop. And I'm guessing that is a vertical block loop. Let's just call it that. Right, let's just have a look. So that, yeah. And there's popping, yes, popping the count, decrementing, end as a JP not 0. I'm guessing it's not doing a DJNZ because it's out of range, because it's an 8-bit offset. But yeah, that's just my guess. Okay, so we want to find out where it's getting this, where the DE is actually getting set up. So let's have a look. So yeah, we've got an address there. Now this is interesting. So we're doing, it looks like there's a multiply by 8 there. Then the result is getting pushed into BC, and then it's continuing with 2 more multiplies. So that would take it to a multiply by 32. So really, so what we've got is we've got a multiplied by 8. We've got the result stored there. We continue to multiply by 32. Then the result, the multiplied by 8, is added back in. So that effectively makes it a multiplied by 40. Now we know the screen is 8 blocks by 5, so that's where the 40 takes place. It's like there are 40 bytes per screen because each byte is a block index. I hope that makes sense. And then we add the offset. So this must be where the screen definitions live. That must be the screen number. And that's right after the attribute memory. So you can see the attribute memory there, isn't it pretty? We can do a label here. I'm guessing this is placed here because this is contended memory, which is a little bit slower, and I think it's placed here because you don't really need to pull screen data out very often, only when you flip screens. So it's a good place. It's a good thing to put here. And these are like 40 bytes each, so it's like 8 by 5. So we could, if we wanted to, we could format this to an 8 by 5 character map. It might not make that much sense, but let's just see what it looks like. Okay, so that's sort of what a screen is like. I guess it doesn't make that much sense looking at it here. We don't really know what screen that is. It might not be one we've visited yet. But anyway, I thought I'd just put that in there. There might be a better way to formatting it. But so essentially what I've showed you here is how to kind of find the screen data and how the screens are drawn. And with this, you could probably, build if you wanted to peek through the data of the game, you could probably build your map up independently, because we found out where all the kind of the map graphics are. There's probably some extra stuff here that we kind of need to find, which is things like how enemies are getting spawned and gameplay objects and things. I'm guessing they're probably a special type of block, and I'm further guessing that it's probably some of this logic is probably got something to do with entity placement, and it's checking for a specific block type. But anyway, I'm going to leave that for now. And what I'm going to do very briefly now, just at the end of this video, is I'm going to kind of show you some other things you can do with the graphics viewer. So we found the background graphics, but what we also want to do is find the sprites. Now, what we can do is you can scroll across the memory with this, and we need to try and find something that looks a bit like graphics. And often you can sort of see if there's a lot of lines and stuff, that tends to be graphical data. And look, we can see it's a bit of Jack there. That's interesting. But let's have a look at this data here. Now what we can do is this view kind of views the whole thing in columns, so you can see with that font there that it's kind of going a character at a time through memory. So as we go down here, we're going down through memory, and then it does another column and another column. So what I can do is I can change how many characters each column is, and that can kind of help us to reveal the data. Now, since I've done that, we can see some shapes are appearing here. So let's try and increment it a bit more. Oh, look. There we go. We can see the sprites now. So what we've got here is we've got what looks like a sprite and a mask next to each other. And as I said before, when it reads memory, it's green. When it writes memory, it's red. So we can see here that this is getting red here. So it's reading in the mask and the sprite for Jack. And as you can see, that one that's green, the most recently read one, is actually the one that's on screen there. So what we can do then is we can find this in memory. If I double click on it, it's also marked green in memory, so we can see this is something that's been read recently. So I think this is probably one of Jack's sprites. So again, we can format this. If you do bitmap, now we know it's four characters across, so that's 32 bits. And then we need the height, which I'm guessing looks like it's 3 characters, so that'd be 24. So let's see what that looks like. There we go. So we can see we've got Jack and his mask next to each other. The mask is first in memory, and then there's the sprite after it. And I imagine if we do format and advance, we can kind of get all the sprites, because they're all kind of next to each other in memory. We've got various other sprites for different entities and things. And then we can see there's that one there, which is like some bat creature thing, which is there. So that's something we can look at. We can look at the code where that's read, and we can see where it's getting written to. If we actually look back at something we saw previously, we can see there's bits of Jack there. So I'm presumably this is the mask getting applied to the background or something like that. So this is a temporary work area where we kind of fetch Jack's sprite, fetch the background, use the mask to combine them together, and then write it out to the screen. Okay, I think I'm going to leave it at that for now. So I hope you found this useful, and I hope it'll help you get started using Spectrum Analyser. I do plan to do some more videos, and if you've got any questions or comments or suggestions, please put them, underneath in the comments. I've had a lot of very good suggestions that have helped me in the past with this project. So, anything is, greatly received. And hopefully I'll do another video soon. Goodbye.